Hello and welcome to our section. Today we will be presenting the paper titled Making Case for Using RAFT in Healthcare through Hyperledger Fabric. My name is Anastasios Alexandridis, and we also have with us Ghassan Al-Sumaidaee, Dr. Rami Alkhudary, and Professor Zilico Zilic. So today we will talk about the problems in data record systems, such as the one found in healthcare, and how blockchain can come to address those problems. We will also talk a little bit about some existing implementations and say that there are many ways to achieve consensus. We will then talk about RAFT and present some background on that. We will continue with our stylized healthcare network example, and in the end we will conclude with a summary of the benefits and with some future research avenues. So let's talk about the problems in data record systems. We have two main problems. The first problem is fragmentation of data, and the second is the single point of failure. So what does this mean? In the context of healthcare, fragmentation of data could mean a patient who goes to a different hospital does not have their data found in their database, because a hospital will maintain a database for their own patients, and another hospital will maintain that database as well. And when the patient goes from one hospital to the other, they have to register again, and they need to replicate this data. We also have single point of failure. What does this mean? That a hospital will typically have a database, and if something happens, they have backups, they can restore data, but the system will not function temporarily. It could be down for maintenance, or a lot of things could happen with it. We also have scalability problems with those databases, and we also have security problems. So how does blockchain address this? So in short, the blockchain can be defined as a distributed ledger or decentralized database of digital records. These are chronologically organized and immutably registered, and a precise consensus algorithm is being used to achieve correctness. So this is what consensus is essentially. It's a way to agree on the correctness of the data. Generally speaking, when we talk about blockchain, we refer to the public blockchain like Bitcoin and Ethereum. And when we talk about consensus, we will talk about mining, as they call it. So what is mining? Mining is a process to confirm that the data is correct, but it's very computationally intensive because we're dealing with a public blockchain where anyone can do that, can propose a transaction. So what about the private blockchain? So in a private blockchain, operators decide to work together to build a network, and this is a limited access network, so they have full control of who can be part of the network, and they can trust that person or entity. So for this reason, they can also define the consensus being used, and there is no need for mining to validate transactions. This is where things get interesting, because consensus does not need to be computationally intensive, and therefore it can deal better with large volumes of data. So let's talk a little bit about existing implementations. So we have here one implementation where we have a decentralized hospital network using blockchain, which is based on proof of work. We have a medical data sharing system based on proof of stake. We have an intelligent healthcare supply chain based on delegated proof of stake. We have a consortium blockchain system using proof of authority. We have a multi-layer intelligent health management system based on practical Byzantine fault tolerance. We also have a blockchain-based multi-stage blockchain, a healthcare system interoperating with wireless body area networks, which is based on a cross-fault tolerance implementation. As we can see, there exist many ways to achieve consensus. So what about RAFT? what is RAFT and why is it important? So, RAFT stands for Replicated and Fault Tolerant. It is a way to achieve consensus, and it's not limited to blockchain. It is a leader-based mechanism. So what is the leader? So, in RAFT, the nodes can have one of three roles: leader, follower, or in the case there is no leader, candidate. A candidate is getting votes to be the leader. So a leader is responsible for interacting with the clients on the network. A client will request something from the leader, and the leader will forward that to the followers for confirmation. The followers are responsible for acknowledging the requests and sending them back to the leader. If a client attempts to contact the follower, they will forward this request to the leader. There are mechanisms to elect a leader and replicate the log across all nodes, achieving consensus safely. RAFT is designed to be easy to understand and implement, and it can really speed up development of blockchain implementations and consensus. But let me be clear, RAFT is not limited to healthcare, right? So they're applicable to any kind of data record system and value chain. So our stylized healthcare network built on Hyperledger Fabric. So here we can see in our network we have several organizations that lack a centralized managing authority. So here we have, for example, hospitals, we have insurance companies, we have the government even. We can have a lot of different participants, and they each maintain a copy of the ledger, one or more copies of the ledger. Because, for example, hospitals, we could have 5 hospitals participating in this network. So they each have a copy, or maybe 2 copies. Let's talk a little bit about Fabric though. So in Fabric, we have peer nodes. So the peer nodes maintain a copy of the ledger and execute smart contracts. We also have order nodes which perform the consensus and assure us that the data is reliable. But what is smart contracts and ledger? I just mentioned these. So smart contracts are actual piece of code that is being executed to interact with the ledger, which itself is a distributed database essentially. So somebody who wants to interact with this blockchain network, they need to interact with the peer, execute a smart contract, which will then interact with the ledger. We also have channels which allow data isolation and confidentiality. And we can think of channels as a different blockchain to an extent, because for every channel, a peer will maintain a different ledger. So, Fabric uses an execute order validate model. Its design relies on deterministic consensus, and any block validated by a peer is guaranteed to be final and correct. Ledgers cannot fork in the way they do in other permissionless blockchain networks. This is important because we need to achieve finality and data reliability. So, as we mentioned, we have peer nodes and order nodes. Now, let's talk a little bit about the flow of a transaction. So, as I mentioned earlier, a peer node will execute a smart contract and interact with the ledger. So what happens if a person, an entity, let's say a doctor, for example, in a hospital, they want to interact with the ledger and either read from it or write to it. So they will use an application to connect to a peer. This peer could be anywhere in this network. And they could also talk to 2 peers if this is required. They will present a certificate to show their identity and prove that they have the permission to execute a smart contract that is found on this peer. Once they do that, the smart contract is executed and the ledger is being accessed. Now, if this person or entity wanted to read something from the ledger, this is returned back to them. However, if they wanted to write something, they will send this transaction to the ordering node afterwards, once the peers have agreed with their change. This then goes to the orderer node, which will check that enough peers have endorsed this transaction, this change, to the ledgers. So as we can see here, for example, we have two transactions. We have transaction 1 and transaction 2. One transaction has received one endorsement because perhaps it's enough for this type of transaction. The other transaction has received two endorsements because this one would require two endorsing peers. These transactions go to the order node, which will then order these transactions into blocks. And here we can see transaction 2 arrived earlier, so the order of the transactions is being maintained. Then, when this block is finalized, it will be sent back to the peers from the orderer node, which will then append it to their ledger. The peers will need to validate this, of course, and if the transaction cannot be validated, they will mark it as invalid. The block will still go in the ledger, but some transactions may not be committed and may not update the database they keep. So, in conclusion, the blockchain is an append-only distributed ledger which is very powerful. We can achieve immutable logging and auditing. We also have cryptographically signed secure transactions, where each entity has to have the correct permissions to execute the transaction. We have trust ensured by relevant parties endorsing transactions. This means that if somebody wants to perform a transaction, they may need multiple peers to endorse that, and multiple peers who are related to this transaction. So these are benefits of blockchain. How about RAFT? RAFT operates quickly and efficiently, as we can see. We have a two-phase configuration when adding or removing nodes to from the network, and this avoids the possibility that we can have two majorities formed during configuration. RAFT is easy to understand and implement, and it can accelerate development. RAFT and blockchain can add value to healthcare applications, but it's not limited to that. Data record systems and value chains can also benefit from it. So for the future work, we would like to make sure that this implementation is feasible. The proposed example is feasible. We would need to include other organizations because thus far we only had the hospitals, but we would like to add, for example, the government, insurance companies, and so on. We need to investigate the cost of implementation and maintenance. We also need to look at further improvements on the security and reliability of data through smart contracts and endorsement policies. We could also look into making sure that, for example, participants of the network cannot be socially engineered, which would result in an attack through, let's say, security tokens. Because very often, attacks come from inside. So this is also something that we would need to ensure is dealt with. Otherwise, what's the point of having a very strong consensus mechanism if an employee can just attack the system from inside, or somebody who impersonates an employee. Further, we need to perform an investigation on the scalability in decentralized systems that integrate big data analytics. Thank you for your attention, and please let us know if you have any questions.